The next piece of equipment that's used virtually for every test in 461 are called line impedance stabilization networks, or LISNs. They are used to control the impedance of a power source during testing. During earlier revisions of the standard, where LISNs weren't called out, test responses or test measurements made at various test labs or locations varied substantially. And what the committee had found was that without the use of a LISN or control of the power line impedance, the amount of emissions produced by that equipment will change. So a line impedance stabilization network is put in line between the power source and the equipment under test to control that to a relatively known value. It actually simulates about 50 meters of power cable, which is the typical length that you would see on some of the largest platform installations. Now, there are some occasions within the 461 criteria, primarily called out in the appendix of 461, where different values of LISNs can be used. Mainly if it's in a smaller application, such as a small aircraft or vehicle, using a low power, a low voltage power source, the 50 microhenries of inductance might actually disturb the operation of the equipment. So there are some tailoring activities that can be used to determine a different value than 50 microhenries, but in general, 50 microhenry LISNs would be used. So as discussed earlier, the power and signal segregation is, as you see here on these non-conductive 5 centimeter standoffs. Each cable is separated by at least 2 centimeters as specified by the standard. The power cabling is actually routed to the LISNs that we talked about, line impedance stabilization networks, one for each individual power phase, routed to the back side of the test chamber and cleaned through power line filters which are attached to the side of the chamber. Now, from the interface from the LISNs to the interface of the equipment under test is approximately 2 meters. The test setup boundary is your 2 meters of exposed cabling to the front edge, including the entire width of the equipment under test. Now, here are a couple typical curves that you would see for the LISN that would be used for 461 testing. To the left is the impedance curve for that LISN. Now, the LISN is 50 microhenries of inductance, so you would expect that starting at 10 kilohertz, the impedance, reactance impedance of that inductor would be fairly low. But as you get up past 150 kilohertz, it really starts to climb in ohmic impedance and start to level out to as high as 10 megahertz. The curve to the right actually shows the correction factor for the measurement capacitor, which is built into the LISN. This measurement capacitor is used to perform the voltage measurements, conducted voltage measurements for CE102, which we'll get to in following test modules or qualification modules. Next would be the ground plane. The ground plane used for Mill Standard 461F testing can either be the floor of the chamber for freestanding equipment or a tabletop ground plane used to simulate the actual grounding impedance of the equipment once installed in the test environment. There are a couple requirements for that. Now, if the actual installation is unknown or multiple installations for this particular product are expected, then the ground plane should be used. Unless otherwise specified, ground plane shall be 2 1/4 meters squared. In larger areas with smaller side, no less than 76 centimeters. When a ground plane is not present in the installation, the UT should be placed on a non-conductive table. As we mentioned, this is all in an effort to simulate as best as practical the actual installation in its installation environment. Now, in addition to that, ground plane shall have a surface resistance of no greater than 0.1 milliohms per square. This relates to a DC resistance between the metallic ground plane and the wall or floor of the chamber to be no greater than 2.5 milliohms of resistance. The metallic ground plane shall be electrically bonded to the floor of the wall, floor or wall of the chamber at a distance or at least once every meter along the length of that ground plane. And these grounding straps shall be made out of solid conductors, straps, with a ratio of 5:1. Now, the reason for that is the Air Force had done a study several years ago that showed because of high impedance or high inductance on circular mill or stranded cabling, could have an effect on the impedance to ground at higher frequencies. So using a copper sheet or copper strap, using a ratio of 5:1 length to width, will help minimize the amount of impedance over frequency. Here's a photograph of a typical 461 setup using floor standing test equipment. In this drawing or photograph, you can see that the equipment is positioned on the floor, spaced at least 30 centimeters from the anechoic material or wall of the chamber. You have your interconnecting cabling routed to the front edge of the test setup boundary in parallel to the front edge of the test setup boundary for at least 2 meters. You'll actually see the lizens on the floor connected to your power lines, connected from there to the equipment under test. This would be your standard test setup used for a certification test, virtually every certification test in 461. Next would be the measurement equipment requirements used to perform emissions testing per 461F. This would cover both conducted and radiated emissions tests. Spectrum analyzers are used to measure and quantify the electromagnetic radiation via conducted on lines, power lines, or radiated off the equipment enclosure and interconnecting cables. Now, when we actually make these measurements, the data received from the measurement antenna or coupling clamp or lizzen would be collected as a raw data element. To make this an actual quantifiable value, factors for that device, that measurement device, would also be included into this data, which we call corrected data. Now, so for instance, if we were making a radiated emissions measurement using a particular antenna across a particular frequency range, we would collect that data through the spectrum analyzer, add the insertion loss or factors for that particular antenna together to create a corrected data element, as you can see in the plot below the photograph of the spectrum analyzer. Now, 461 specifies and requires that all data collected for emissions testing be plotted and corrected automatically through software. We currently use, NTS worldwide, use what is called TILE software, or totally integrated lab environment software, to do that. Now, the emissions bandwidth and measurement times are specified by 461. This table that you're looking at breaks down the individual frequency ranges from 30 hertz to above 1 gigahertz. And they're used to standardize how many data points are taken per particular frequency range. Larger bandwidths than shown here are allowed, but are not allowed to be corrected for. The larger the bandwidth you use, the higher the electrical noise floor may be for that measurement. Bandwidths are specified here as the 6 dB point, not as the 3 dB point in commercial requirements. What this typically means is that how the spectrum analyzer determines an actual peak. The wider resolution or filtering bandwidth on the spectrum analyzer would typically be, for commercial environments, from 3 dB down from the peak on either side of that frequency response. Mil standard 461 requires the frequency response to be from the peak down 6 dB from either side of that frequency. Video filtering is not allowed. Spectrum analyzers shall be set to the highest frequency value, typically 3 megahertz or above. This allows full response of the frequency characteristics across the test range. Now, there are two types of measurement equipment, spectrum analyzers or receivers, that can be used. And 461's table breaks out the requirements for both. The first is an analog measurement device. Shall use the measurement times for each frequency range, as you can see here. These sweep times are calculated by determining the test frequency range multiplied by the minimum measurement time. So for example, if we were making a sweep from 10 kilohertz to 150 kilohertz, we'd have a total range of 140 kilohertz. We take that 140 kilohertz, multiply it by the 0.15 seconds per kilohertz, and come out with a total test time of 21 seconds for that range. The alternative is a digitally synthesized measurement device, or an EMI receiver, shall step in half bandwidth increments. As you can see, the 6 dB bandwidths would be broken into half or less while observing the specified dwell times for each frequency range. These sweep times are calculated by determining the test frequency range divided by half measurement bandwidth multiplied by the dwell time. So for example, we take a 10 kilohertz to 150 kilohertz range, again 140 kilohertz. 140 kilohertz divided by 500 hertz gives you a 280 steps across that frequency range. 280 steps multiplied by the 0.015 seconds per dwell time equals an approximately 4.2 second measurement sweep rate. Now there's an alternative test method as well. And this alternative method is relatively well defined in Mill Standard 461F. It was talked about in earlier revisions of 461, but it really covers multiple fast sweeps, maximum hold scanning. Typically used when you have a device which produces intermittent signals with low frequency duty cycle rates. These types of signals can be missed during a conventional scanning method. It can also be used for equipment that has very short cycle times, such as an actuator or a door or a valve of some sort. Multiple fast sweeps can be used where you can sweep that entire frequency range very fast, but using multiple sweeps across that range until you capture the total frequency response for that particular range. Now, although the sweep time is increased, the minimum dwell time specified per tune frequency is maintained by increasing the number of sweeps per range. So as you can see in this table, if you had a sweep time of 291 seconds, this would equal the single fast sweep time of 0.194 seconds multiplied by the number of sweeps. So it would equate out the same as using the conventional emissions measurement method. Now talking about susceptibility testing, scan and step rates for 461F. What we have here is the rates and step sizes are specified in terms of a multiplier of the tune frequency, commonly referred to as F0. Of the signal source. Now again, for analog sweeps refer to signal sources which are continually tuned across the frequency range. Step scans refer to signal sources which are sequentially tuned across that frequency range. Now scan rates and step sizes shall be decreased when necessary to permit observation of a particular response. And this is again based on the operation time or cycle time of that equipment. Key thing to point out is that the sweep and step times above 1 gigahertz has been changed from Mill Standard 461E to Mill Standard 461F. They've actually relaxed the requirement due to probability of susceptibility detection at wider and faster rates. This really has equated to a reduced test time between 1 and 40 gigahertz to approximately 2.6 times that specified in 461E. So we'll break it down for you. An example of an analog scan would be a typical range 30 megahertz to 100 megahertz. You have a total span of 70 megahertz. You would also start at your initial F0 of 30 megahertz, the start of the frequency range, multiplied by the rate of 0.00333, which equals 999 kilohertz, or 100 kilohertz. 70 megahertz divided by 100 kilohertz equals 700 seconds, or 11.6 minutes for that entire test duration. Note that the calculation is based upon F0. Recalculating the sweep rate multiple times to that frequency range will reduce the sweep time. So I mean by that, the higher the frequency, or F0 is, the faster the sweep rate becomes. And I can give you an example of that. Using the step scan method, a continuously calculated step rate, 30 megahertz to 100 megahertz, using the 30 megahertz as your initial F0 multiplied by 1 times 0.005 gives you a step increment of 30.15 megahertz. The next step would be recalculated at 30.15 megahertz being your F0, multiplied again by 1.005 equals 30.3 megahertz, and so on and so on. The total number of tuned frequencies for this range would be 242 steps multiplied by a dwell time, a specified dwell time of 3 seconds, equals 726 seconds or 12.1 minutes for that entire range. Each tuned frequency shall be dwelled on for 3 seconds as a minimum, specified by 461, but is dependent again on the actual cycle time of the equipment. What I mean by that is that the bit software used to validate the equipment's operation performance, if that cycle time is greater than 3 seconds, that dwell time per tuned frequency must be extended to match, at a minimum, that particular cycle time. And any extension from 3 seconds will have an impact on the actual test time or test durations. This concludes Module 1, General Requirements for Mill Standard 461F. Following this will be a short quiz, so good luck and hope to see you soon.